Hello everybody, welcome back. Just go through a quick presentation here for our map projections. Now, the reason I want to go over map projections for our human geography unit is, while this may seem very inconsequential, we have to go over the science of map making. Now, you'll see this on pages 6 and 7 in your textbooks, kind of like the science of it, how it got started, the first maps. You'll see some examples there of what they look like. But I'm going to show you some of the contemporary maps that are used today and how they are, brought forward as a, possible solution to taking a spherical object and then laying it flat on a two-dimensional, piece of paper, whether it's a chart or a map, whatever it may be. How do you take that 3D object and put it on a flat 2D, piece of paper? And something, if you want to do this on your own, this is not mandatory for you to do, but if this is something that you are interested in doing, if you have like an orange or a nectarine at home, what I want you to do is I want you to try to take that spherical object, peel, not nectarine, tangerine, take the orange or the tangerine, peel that object, and try to create a map or at least a particular flat surface to make that look as, relevant as possible to what you're seeing in that 3D object. If you want to ahead of time, you want to draw on that, like if you want to use like a washable marker or something like that, you can draw on the skin of that orange, like draw a map of the world to the best of your abilities, and then try to peel it to create a 2D object like you see here on the screen. All right, but I want to go over different projections for you because each of them try to solve a problem that another map, another projection might have. I'm going to post a video from the show West Wing that goes over this as well about why people argue different things for maps and why they make different cases for why a certain map should be used and why others should be ignored. But the one that most people like to follow, and this is what we see mostly on maps around the continental United States, is the Mercator projection. This is a German scientist who, obviously from Europe, used the map to the best of their abilities to create a projection that looked pretty familiar to what we see. And again, when he first created this is what made sense to him. But if you look as close as you get to the north and south poles, you see that the lines of latitude get further apart. The longitudinal lines stay relatively the same. All right, but the longitudinal lines go further apart. This is a flaw. Someone said that what it does is it creates a top-down theory, that those in the developed world in Europe saw themselves as superior than those below. This is an argument as to why people don't like that. All right, because if you look at Greenland, it looks roughly the same size as South America, if not bigger, if not the same size as Africa. But Greenland in reality is probably 1/4 to 1/8 the size of South America. So the problem you have with this is that it enlarges the sizes of particular continents or bodies of land that should not be that large. You look at Iceland here. Iceland looks as large as the northeastern part of the United States. It is not that large. All right, so this is where we begin to see some issues here with Mercator. All right, the next projection that we look at is an attempt to try to react to Mercator directly, and that's the Gall-Peters projection. You can see that the closer you get towards the poles, especially the North Pole, you're going to see a much more condensed map. All right. Now, this may show you a more representative projection when it comes to size, but you're really doing yourself a disservice when you're trying to find locations on a map. Like if you had to scroll in to this map, right angle will not be a right angle, which if you went to Mercator, if you drew down on a map, if you made a right angle on a street, like a street corner, it would still be a right angle on this map. It would not be here. All right. So you're looking at accuracy of specific location here, but inaccuracy of size, especially when you get closer to the poles. But you're looking at accuracy of size here, but inaccuracy of exact location and direction. All right. This is where you're really beginning to see some of the major changes. Now we're going to get to some really crazy ones here. Gauss-Kruger decided why do we have to focus on the equator? Why can't we put the equator, while it's in the middle still, the poles are still seen and you can see the entire Earth still. It takes this 3D object and I think it makes more sense out of how do we turn this into something that can be represented better on a two-dimensional like piece of paper or a screen. If you look at this map, you can definitely see South America is extremely inflated for size. Central America is extremely inflated. Heck, you got Panama pretty much stretching across the entirety of the United States, which is Panama's right here. All right, stretching across the entirety of the United States. You have Russia Europe up here, India's ginormous. You have Sri Lanka that's the same size as Spain and Portugal, which it is not normally. Africa is extremely small because this is where the map kind of centers. Then you have Australia upside down, you see Antarctica, but this looks at the views from the poles. All right, if you were to look at the north-south particular dimension there, and that gives you that projection. Again, definitely odd. The good homosyline, excuse me. This definitely looks like this was peeled from a globe, but you can kind of still see that there's a two-dimensional riff here that, while there seems to be accuracy with, size here, you look at some of the longitudinal lines, they are crooked, and you're going to have crooked lines on different parts of those streets as well. Again, very inaccurate when looking at the location of places. The next is the Wagner. This is the map when I show you in my room. This is the map that I have. This is a really good estimate as to how we can see maps in this way. But this was utilized as a way to show true size to the best of the abilities, while also giving a nice, easy layout of the world. All right, that you have one continent, the Americas on the west, which is the Western Hemisphere, which is what was discovered by the Europeans who are on the eastern side. So this is like the known world, and this is the as of 1492, and then you have what's known after that on this side. So definitely very easy to understand map projection, and it definitely shows you the spherical and the accurate sizes. Even though you do see some stretched out longitudinal lines here. All right, but or latitudinal lines, excuse me. You have a very good representation, a better representation, obviously, of size than you would with Mercator. And this one was created and actually won an award in the Japanese map making competition to see who could create the best projection for maps, to look at size, to look at shape, and also to look at accuracy throughout the maps. This is the one that won the competition. This is called the Orthograph World Map. You can look this up online if you want to and do some more research on it if you like, but this is one that provides that explanation. Hey, this is a map that shows accurate size. It gives us an idea that this is a 2D object that's taken from a 3D object. You can see like the distortion of the angles that you see there based on what we're used to seeing. It shows Antarctica in its fullest and relative accurate size compared to everything else. When on another map like this one, we see Antarctica as ginormous, the size of the entire Earth looks like, which it is not. So you definitely have some accuracies throughout here in size, and you have the full projections of certain continents you wouldn't normally get from other maps. And if you go back to Good Homosyline, while you have accurate size, probably here in landmass, you're probably not getting a lot of, you're confused as to where different parts of Antarctica are. Not saying we're trying to, plan a vacation in Antarctica. It's just, you want to be able to see the whole entire thing. All right, this allows that. All right. I just want to go over these map projections because if you look at the science of map making, it is completely imperfect. There's probably not going to be ever a perfect way for us to see a map. And when we go back to Mercator, one other part I wanted to mention with this is the map that a lot of navigators used at sea when they're navigating their ships across the ocean. Because in this map, like I said, it is about true direction. Eventually, because this is flapping the Earth as a spherical object, when you go into a certain direction, you're not going a true straight distance to that map. You're not going from from one point to another in a straight line. You're actually going in an arc, which takes you longer, but at least at that point it's an accurate heading. All right, so you're not taking the fastest route here. You're taking the most accurate, which is what's important about Mercator. But then as Mercator kept being used, we looked at inaccuracy of size, the idea that this top-down mentality, showed how inferior the developed world thought of the developing world. It's just those social things that happen when you get that, ability of top-down. And again, you could look at this map and flip it upside down. It's all about, perspective, all about the projection. The Earth's still there. It's still the same bodies of land, but it's all about how you're looking at it. All right, so this is what we have here. There's some other videos I'll post about this, and there might be a discussion board I post about these coming up this week. So something you can complete and look at and discuss with your fellow students. just as to what you think is the best. Again, you go back, you can take a look at Mercator, Gall-Peters, Gauss-Kruger, Good-Homosyline, the Wagner 4 map, and the orthograph. These are different attempts of people to try to, lay the world on a flat piece of paper. All right, how did it work? All right, so do your, look through these and go about that, and hopefully you have a good time with this and see kind of how difficult it is to really create a map of a 3D object. All right, so if you want to do that project with an orange, it's not really graded. It just helps you kind of visualize how difficult it really is. All right, thank you for your time, everybody. There might be some more videos to come, so do your best to watch those as you can. Thank you.